Foundational Large Language Models, LLMs, and Prompt Engineering. Welcome to our Foundational LLMs and Prompt Engineering training. By the end of this training, you will understand what LLMs are and how they work, know how to craft effective prompts, use prompt engineering to improve AI output, explore real-world applications of LLMs and prompt engineering. Here are the most critical topics and how to apply them. Learn about foundational LLMs and their architecture. Definition and architecture of LLMs. Difference between traditional NLP models and LLMs. Examples: GPT, Palm, Llama, Claude. Explore how LLMs are trained effectively. Training processes including pre-training and fine-tuning, instruction tuning, and RLHF. Ethical considerations: bias, hallucination, data privacy. Understand the fundamentals of prompt engineering. What is a prompt? Importance of phrasing and structure. Prompt types: zero shot, few shot, chain of thought. Apply prompt engineering to various scenarios. Real-world use cases for LLMs. Writing code, academic research. Language translation with control. Resume creation or content generation. Discover tools and resources for effective prompt engineering. Prompt marketplaces and AI APIs. Prompt templates and chaining. Downloadable resources. Prompt template starter kit. Now let's check our knowledge retention with a couple of real-world example scenarios. Consider how LLMs can assist in real-world applications. Using LLMs for chatbots, code generation tasks. Your action should be: summarize an academic paper. Explore how prompt engineering can enhance LLM output. Language translation with control, generating business ideas. Your action should be: create a prompt for generating a business idea. Now let's recap on what you learned and what you need to remember. The significance of scaling in LLMs. The importance of prompt phrasing and structure. Ethical considerations in AI usage. Practical applications of prompt engineering. Comment which LLM you've interacted with the most. Let's deepen our understanding together. Thank you for being a part of our foundational LLMs and prompt engineering training.
Embeddings and Vector Databases. A deep dive. 1. What are embeddings? Embeddings are mathematical representations of data, words, sentences, images, audio, code, etc. in high-dimensional vector space. Their core purpose is to capture semantic meaning in a way that similar concepts are mapped close together. Characteristics of embeddings. Dense vectors. Unlike sparse one, hot vectors, embeddings are dense and compact, e.g. 384D or 768D vectors. Context-aware. Modern embeddings, e.g. from BERT, OpenAI, Cohere, consider surrounding context for richer meaning. Modality agnostic. Text, images, and even audio can be embedded into a shared vector space. Examples of embedding models. OpenAI embeddings, text embedding, Ada 2. Sentence BERT, clip for images and text. Fast text, Word2Vec, older models, cold use cases. Semantic search, similarity detection. Recommendation systems, clustering and classification. Knowledge graph enrichment. Number 2, what are vector databases? Vector databases are specialized data storage systems designed to efficiently store, index, and search embeddings. They enable similarity search operations like K nearest neighbor, KNN, approximate nearest neighbor, ANN, cosine similarity, Euclidean distance. Instead of querying with keywords, users query with a vector, and the database returns the most similar items by computing vector proximity. Popular vector databases: name, description, open source, Pinecone, cloud native, scalable, hybrid, storage. No. Phase, Facebook, AI similarity search, yes. Weaviate, supports hybrid, text, Geom, vector, search, yes. Milvis high throughput, distributed, yes. QDrain optimized for real-time similarity, yes. Redis vector search on top of Redis, yes. 3. How they work together. Embedding, Geom, Vector DB workflow. Data ingestion. Raw text, images, or structured data are converted into embeddings via an embedding model. Storage in Vector DB. The embedding vector is stored alongside metadata, e.g., ID, tags, original data. Querying. When a user inputs a query, e.g., AI used in agriculture, it is converted into an embedding vector. Similarity search. The vector database returns the most semantically similar items, top K vectors, using distance metrics. Optional RAG pipeline. Combine retrieve results with an LLM to generate accurate, grounded responses. 4. Why are they important? Scalable semantic search goes beyond keywords to understand intent and context. Personalization enables context, aware recommendations, and search results. Efficient RAG forms the foundation of retrieval, augmented generation, e.g., ChatGPT with custom knowledge. Multimodal AI unifies text, images, and other data types for integrated search experiences. RAID RN5 Key distance metrics. Metric description use case. Cosine similarity measures angle between vectors. Text similarity. Euclidean distance measures direct distance in vector space. Image or numeric embeddings. Dot product fast inner product comparison optimized ANN search. 6. Example. Semantic search system. User query. Best AI applications in healthcare. TEP step 1. Convert query to embedding. TEP step 2. Use Pinecone to search top 5 closest document vectors. TDA. Step 3. Retrieve matched content with metadata. AT. Step 4. Optionally send context to LLM for generating a response. 7. Architectural use in AI systems. Search engines. Power search in AI chatbots, like U.com, Perplexity AI. Recommendation systems. Suggest similar products, videos, or articles. AI assistants. Feed contextual documents to LLMs in corporate, legal, or medical settings. RAG systems. Use vector search to ground LLMs with trustworthy data. 8. Challenges and considerations. Dimensionality. High-dimensional vectors, e.g., 1024D, require optimized indexing. Latency versus accuracy, and sacrifices some accuracy for faster response times. Data freshness. Updating vector databases regularly is crucial. Security, compliance. Embedding user content requires privacy safeguards. 9. Future trends. Hybrid search. Combine lexical, keyword, and semantic embedding, search. Multimodal vector stores. Unifying audio, text, image vectors in one space. On-device vector DBs. Lightweight retrieval for edge AI applications. Self-updating embeddings. Continuous learning for dynamic use cases. Generative agents and agent companions, vertical bar exploring the next evolution of human-AI interaction. Welcome to TechBook, your trusted source for cutting-edge insights into artificial intelligence, emerging technologies, and the future of intelligent systems. In this compelling episode, we unravel one of the most transformative concepts in modern generative agents and agent companions, redefining how machines interact with humans in deeply personal, contextual, and adaptive ways. What are generative agents? Generative agents are AI-powered digital entities capable of simulating human-like cognition, memory, personality, and decision-making. Unlike traditional chatbots or assistants, these agents use large language models, LLMs like GPT-4, combined with structured memory systems, behavioral graphs, and reinforcement learning to simulate real-world human-like behavior in virtual and physical environments. TED. They can reason, reflect, recall, and adapt. K. They behave autonomously based on evolving internal states. AGA. They are used in simulations, productivity tools, gaming, healthcare, education, and more. Imagine a virtual roommate who remembers your preferences, adapts to your mood, and grows smarter every day. That's the power of generative agents. Who are agent companions? Agent companions go a step further. These are personalized AI companions created to offer emotional, intellectual, or task-based support. From virtual mental health assistants to AI-powered study buddies and storytelling partners, these agents are designed for connection. Some examples include Replica, AI friend with emotional memory; Character.ai, chat with fictional or historical personas; Pi.ai, a calm conversational assistant; virtual NPCs in AI-driven games with evolving backstories. These agents use long-term memory, vector embeddings, emotional recognition, and natural language understanding to build rapport and grow closer to their users over time. How they work, a peek behind the curtain. We break down the architecture and components that make generative agents intelligent. LLMs, large language models, the brain behind conversation and context. Embeddings and Vector databases, store and retrieve long-term memories based on meaning. Behavior trees, finite state machines, decision logic for dynamic actions. Simulated environments, like Stanford's generative sims, where agents interact socially and autonomously. Feedback loops and RLHF, agents learn from interaction patterns and optimize behavior. Real-world applications of generative agents. Gaming in virtual worlds, lifelike NPCs who evolve over time and interact with each other. Smart homes, proactive AI assistants that manage your home, health, and schedule. Education, AI tutors that personalize content and grow alongside the learner. Mental wellness, agents that listen, counsel, and provide cognitive support. Social simulations, AI citizens in virtual towns for urban, policy, and behavioral modeling. UAT ethical and social considerations. As we explore this frontier, we must ask, how do we prevent emotional overdependence on AI companions? Who controls the memory and behavior of autonomous agents? Can digital agents develop biased worldviews? What's the line between simulation and manipulation? We highlight ongoing research in AI alignment, explainability, bias mitigation, and responsible deployment of generative agents in sensitive domains. How to build one. You'll also get a brief walkthrough of frameworks and tools like Eugene Langchain, UAET Auto GPT, One Meta GPT, GAN, Crew AI, Vaby AGI, ComPinecone Weaviate Vector DBs, Chamber 19 Streamlit plus LLM APIs, UI, and logic. Build your own digital friend, life assistant, or autonomous task doer using these powerful open source stacks. Who should watch? This episode is perfect for AI developers and researchers, students and educators in machine learning, UX designers and conversational AI, futurists and digital philosophers, anyone interested in the future of AI plus humanity. Domain-specific large language models, LLMs. What are domain-specific LLMs? Domain-specific LLMs are specialized versions of large language models that are either built from scratch using corpora from a particular domain or fine-tuned from a general-purpose model like GPT, BERT, T5, etc. on domain-specific datasets. These models are optimized to understand the nuances, data structures, semantic relationships, and specialized language within a specific knowledge domain, e.g., medicine, law, engineering, finance, architecture and training approach. Base model selection. Start with a foundational model, e.g., BERT, GPT-3, T5. Choose a base architecture that aligns with the type of tasks, e.g., classification, generation, QA, pre-training or fine-tuning. Pre-training from scratch using massive domain-specific corpora, e.g., medical records, patents, research articles. Fine-tuning using transfer learning from general-purpose LLMs to save resources and retain general linguistic knowledge. Data sources. Academic journals, e.g., PubMed, ArcCiv, IEEE, Explore, legal documents, court judgments, contracts, financial reports, stock exchange filings, technical manuals, code repositories, industry reports, model adaptation techniques. LoRa, low-rank adaptation, lightweight fine-tuning technique to specialize LLMs efficiently. Prompt tuning, adapter layers, efficient parameter tuning for fast domain adaptation. Reinforcement learning with expert feedback, RLEF, a variant of RLHF adapted to domain expertise. Deep dive into use cases and applications. 1. Healthcare, biomedicine, medical diagnosis support, interpret symptoms, assist in differential diagnosis. Clinical decision support, recommend treatment plans using patient history. Literature analysis, summarize complex research articles. Medical chatbots, HIPAA, compliant virtual assistants. Example, BioGPT, Microsoft. Fine, tuned on biomedical literature. MedPal M2, Google, designed for medical question answering. 2. Legal and policy. Case law summarization. Extract relevant case points. Legal document drafting. Generate or review contracts and policies. Regulation analysis. Understand government regulations in plain language. Example, LegalBert, trained on European legal documents and case law. 3. Finance and business intelligence. Market prediction analysis. Parse and interpret stock trends, investor sentiments. Financial document parsing. Automate understanding of earnings reports. Credit risk assessment. Analyze customer history and suggest creditworthiness. Example, Finbert and Bloomberg GPT, specialize in financial sentiment and analytics. 4. Scientific research and engineering. Hypothesis generation. Aid researchers in forming new hypotheses. Scientific writing assistance. Language, polishing, and structuring. Simulation modeling, design help. Convert technical queries into useful code, snippets. Example, Cybert, Allen AI, trained on scholarly publications. Camberta, tailored for chemical and molecular language. 5. Education and academia. Personalized learning tutors. Domain-aware tutoring, based on learner's pace. Academic content generation, quiz creation, note summarization. Scholarly review bots. Analyze thesis drafts or research manuscripts. Example, EduGPT, custom models, fine-tuned on academic curricula. Benefits of domain-specific LLMs. Feature benefit. Specialized language accurately interprets complex terminology. Improved contextual understanding, reduces misunderstanding of domain nuances. Increased trust domain users rely more on relevant and factual output. Efficient task automation speeds up repetitive or research-intensive processes. Yon, challenges and limitations. Data scarcity. High-quality, labeled domain data is often hard to access due to confidentiality or cost. Bias propagation. Domain-specific models can reinforce biases present in their training data, e.g., outdated practices in medicine, Overfitting risk. Fine-tuned models may lose generalization and fail outside narrow context. Maintenance overhead. Requires constant retraining to stay updated with evolving domain knowledge. Compliance. Ethics. Especially in domains like healthcare and law, regulatory compliance and ethical use are critical. Future perspectives. Multimodal domain models. Combining text with images, scans, tables, or code, e.g., radiology, Jiawan, reports. Personalized LLMs. User-centric models that adapt to specific practitioners, firms, or researchers. Federated domain LLMs. Privacy-preserving training across institutions without data sharing. Explainability and trustworthiness. Integration of XAI, explainable AI, to provide justification for outputs. Open source domain models. Democratizing access to high-performance domain models, e.g. PubMed GPT, LegalBERT. Summary. Domain-specific LLMs are revolutionizing how knowledge-intensive sectors operate. They bring precision in interpretation, depth in domain context, speed in automation, and scalability in decision-making. By intelligently integrating these models, businesses, researchers, and institutions can unlock new frontiers of productivity and innovation. By intelligently integrating these models, businesses, researchers, and institutions can unlock new frontiers of productivity and innovation.